Part A starts by asking you to find g prime of 5. This part is very straightforward. You have a calculator, so you use your calculator to find the derivative. Make sure that your calculator is in radian mode, and also when you write your answer, make sure that you go out at least 3 place values. Finding the derivative evaluated at 5 out 3 place values gave us our first point. The second part of Part A says to use correct units. Usually you do not need to label your answer on the exam unless, however, they specifically ask you for a label. So it says using correct units. The interpretation part, we need to put it into the context. Okay, so let's begin by just reminding us of the relationship between position, velocity, and acceleration. The label up here says tons per hour. A label of tons per hour is a label you would find on velocity. So g of t is a velocity function. When you continue to read and you see that at time 0 we have 500 tons, that is a point on the position function. Tons is a label for a position function. Moving between position, velocity, and acceleration, to go from position to velocity, you take a derivative, and to get from velocity to acceleration, you take another derivative. If I wanted to go from acceleration back to velocity, I would integrate, or from velocity back to position, I would integrate. Okay, so let's start with each piece. The derivative symbol, just some keywords, rate. The negative, when we are interpreting, we always want to use a word that describes the positive or negative. So the negative is decreasing. When I take the derivative of g, and g is a velocity function, I'm going to get acceleration. So the 24.588 is going to have a label of tons per hour squared. When you put in labels, you always want to label your input and your output. We have labeled our output 24.588, but we have not yet labeled the input, which is 5. So it's going to be the rate at time 5, and the label that we're looking for here is hours. So at 5 hours. Okay, this is the main part that needs to be here, but we're going to put in some connecting words. So the rate the gravel is arriving is decreasing by 24.588 tons per hour squared at time 5 hours. Notice all of the key elements are there. The derivative, we said rate. The negative, we said decreasing. The label on the output answer is tons per hour squared, and the label on the input 5 is hours. For this answer, you would receive 1 point, which is the interpretation with labels. Part A was worth 2 points. Part B, find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. Total amount of unprocessed gravel. If we just think of an example answer, so many tons arrived. The kind of label that is on tons is a position. So ultimately we want a position. The given information in this problem is g of t, which is a velocity function, the rate of unprocessed gravel. To move from a velocity function to a position function, you integrate. So I'm going to integrate g of t over the time 0 to 8, and that's going to give me the amount of tons from time 0 to 8. Grabbing my calculator, making sure I'm in radian mode, we integrate, and I get this out 3 place values. I do not need to label my answer. So they gave 1 point for setting up the integral. Please make sure when you set up the integral that you put your bounds, so 0 to 8, you put your function, in this case g of t, and you also don't forget the dt in this case. The final answer, 825.551, gave another point. Is the amount of unprocessed gravel at the plant increasing or decreasing at time 5 hours? Show the work that leads to your answer. We really need to compare how fast the gravel is arriving to how fast the gravel is being processed. The rate the gravel arrives was the g of t function. Another sentence in the original was that the rate the gravel was being processed was at a constant rate of 100. We want to compare these rates at time 5. If I substitute 5 into g of t, I get this 98.140764. No matter what number I substitute into a function that is just a constant value, in this case 100, I get out that constant value, so I get out 100. If you think about what this means, at time 5, the rate the gravel is arriving is 98.1-ish tons per hour. And then the rate the gravel is being processed is 100 tons per hour. So in other words, the plant is processing more than what is coming in. It's keeping up with the trucks that are delivering this gravel. So the gravel is being processed faster than it is arriving. So the amount of unprocessed gravel at the plant is decreasing at time 5 hours. That pile is getting smaller and smaller because it's processing faster than it's arriving. Comparing the answer to g of 5, which was that 98.140764, to the number 100 gave a point, and then the correct conclusion gave another point. Lastly, part D, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on that workday? Okay, maximum, maximize. We learned how to maximize. It's an absolute extrema. If you want to figure out the maximum, then you want to create yourself a primary function. And the primary function is always whatever it is that you are trying to maximize. We want to maximize the amount of unprocessed gravel. So the primary function is going to be the amount of unprocessed gravel. We're going to need to build our own equation that represents the amount of unprocessed gravel. So if we think about what contributes to the amount of unprocessed gravel, the plant, before it even opens, has some unprocessed gravel sitting there. So the amount of gravel that's there when the day starts is going to be in that pile. Then there's constantly trucks bringing in gravel, and the amount of gravel that those trucks are bringing in is also going to contribute to the amount of unprocessed gravel. But the pile is going to be going down because we're subtracting out the amount of processed gravel. So at any given moment, if we had the amount of gravel at the beginning of the day plus the amount that trucks had brought in by then, and we subtracted out the amount that had been processed by then, we would have how much gravel is sitting there. Okay, so how are we going to figure out the amount the day starts with? It told us that the plant at time 0 had 500 tons. The amount that's brought in was that integral that we set up. T is any time, so from the time the plant opens at time 0 to some time, and I have g of x dx, not g of t dt, because I used a t for my upper bound, and I don't want the x and the t to match here. The amount of processed gravel will be minus 100 T. For example, at 1 hour, they would have processed 100 tons, at 2 hours, 200 tons, and so forth. The potential mins and maxes are the numbers that make the derivative equal 0 or undefined. Because this is an absolute extrema problem, we also need to consider the endpoints. So eventually the endpoints times 0 and time 8, because that's the beginning of the workday and the end of the workday. But right now we need to find the derivative of this function we created and figure out where it equals 0 or undefined. I only wrote 0 because this function's derivative is not going to be undefined. Okay, so finding the derivative of 500 is just 0. The derivative of an integral, technically that is the second fundamental theorem of calculus. You substitute the upper bound, so that would be g of t, times the derivative of the upper bound, the derivative of t is 1, minus substitute the lower bound 0, so that's g of 0, times the derivative of the lower bound, but the derivative of 0 is 0, so the back half is gone. So we really are just going to substitute the upper bound times the derivative of the upper bound, which is 1. So we have g of t times 1, which is g of t, and then the derivative of negative 100t is minus 100. Setting this equal to 0, we can grab our calculator and graph this function g of t minus 100. And make sure your calculator is in radian mode. If you graph the function g of t minus 100, I only care about what's going on between time 0 and time 8 hours. There happen to be two x-intercepts. There's an x-intercept at 4.92348 and another x-intercept at 10. Again, I really don't care about the x-intercept at 10 because it's outside of 0 to 8. Now that I have my potential mins and maxes, even though I know I'm going to throw out 10, and I also know I need to consider the endpoints, we want to maximize the unprocessed gravel. So here are a bunch of times where we might have the most unprocessed gravel. To decide which time gives us the most unprocessed gravel, we just need to substitute these times into our position function, which represents the amount of gravel. We can use our calculator to help us do that. Substituting times 0, we have 500 tons of gravel because that's how much was at the plant at time 0. If we substitute 4.923 hours, there's 635.376 tons of unprocessed gravel. Substituting 8, we get 525.551 tons of gravel. I'm not going to bother substituting 10 since it's outside of our domain of during when the plant is open. And the value that's the biggest here is 635.376. Going back to reread the question, what is the maximum amount of unprocessed gravel? It doesn't say at what time it happens. This is what is the maximum amount. We're going to say the maximum amount is 635.378. I could just circle really big 635.378. Circling your final answer is kind of the universal, a circle is the universal symbol for this is my final answer. Setting a prime of t equal to 0 gave 1 point. The answer 635.378 gave you a point. The justification is all of this work, specifically substituting in 0, 4.923, and 8 into our primary function so that we could decide which one was the biggest. And also figuring out that my options for substitution were 0, 4.923, and 8.